this is that. Today we'll now be doing another MAT video of question 3, 2018. So we have a function here and we're going to do some calculus on it. So a chord, what's a chord? It's not musical chords. It's this kind of chord. The type of chord where you take a curve like a circle and then you take the curve between 2 points. It actually works for any curve in general. So sketch the graph. So I'm lazy to actually hand sketch because my hand sketching skills are bad. So instead, let's plot into decimals instead. As you can see, the graph has already been nicely done for you, and this graph will actually solve the next question. Write down expressions for mx in the two cases x is greater than 0 and x is less than 0. This one we have to do a bit more work. So this chord is often called the secant line in calculus, and what we have to do is going to use the rise over run method because we can't actually do calculus on chords. So there we go, x squared minus 2x plus 1 minus 2 over x equals to x squared minus 2x over x equals to x minus 2. There, we done it. And in the case x is less than 0, we may have to do more calculus, but we'll have to use the symmetry on the graph. As you can see, this graph is odd. It's called an odd function around around y equals to 2. And this means that if we draw a random line, say y equals to x, y equals to x plus 2, then you will see here that it passes through this point, and this point. So this means that the gradient, when x is less than 0 is minus x plus 2. Great. Wait, it's actually minus x minus 2. Am I lost? Yeah, it's minus x minus 2. Okay, so show that mx plus 2 equals to x. So that means basically when we plus 2 to this, we become x. When we plus 2 to this, we get negative x. There, done. Explain why g has the negative 2 at 0. So basically when we write this in math language as limit x to 0, x minus 2 equals to minus 2, and limit x less than 0 minus x minus 2 equals to minus 2. Now all of you may be protesting, but we don't use limits in the MAT. Well, you can actually do the calculus for it, but I'm just using limits because I feel it might be a more mathematically elegant solution. So suppose that p is less than q and the hs is the cubic. Show that x prime x is less than 0 and I'm going to p x q. So it has a maximum at p and it has a minimum at q. So we're going to draw a little line here. And look, the gradient is all negative. We can actually prove this using algebra. So we're probably going to do it. H prime x equals to a x minus p x minus q, where a is some constant. So this means h prime x, where x is greater than p and less than q. So this side will actually be positive and this side will be negative. Got that? So that means this is the only place where the gradient is negative. Of course, if the a was negative, then this would be a totally different story because that will be the only place where it's positive. And see that line segment in the middle? That's called the point of inflection. So you can actually use this using calculus. This often involves a second derivative denoted as d squared over dx squared. And then you have to find all the solutions of d squared over dx squared equals to 0, and usually on a cubic there's only 1 because it's a linear equation. Sometimes the cubic can have no stationary points or just one stationary point, which is a point of inflection. Enough digressions already. So that's basically all the cases for cubics. So suppose that c and d are real numbers and that there is a cubic with a maximum x is negative 1 and minimum at x equals to 1. So this means h prime x equals to a x plus 1 x minus 1 equals to big A x squared minus 1, and then c h prime 0 equals to minus a. So this means a equals to 3c. And now we're going to expand our little brackets here. So this means h prime x equals to 3c x squared minus 1 equals to 3c x squared minus 3c. So this means hx, we're going to do the integration move. So it's cx cubed minus 3cx plus d. There, we found our cubic. Yep. So that c is greater than 0 and find a formula for h of x. We have actually done this already. So we killed two birds with one stone. We have already solved question 5 and question 6 at the same time. And now show that there are no values for c and d such that the graphs of y's, gx, and y's, hx are the same. So this means that we have to let d equals to 2. And since g prime naught equals to negative 2, h prime naught is also negative 2. So this means c equals to 2 over 3. Now we are going to calculate g1. g1 equals to, let's use our defining formula, 1 minus 1 squared plus 1 equals to 1. However, h1 equals to 2 over 3 minus 2 plus 2 equals to 2/3. So, therefore, we found a counterexample that is approved by contradiction. So, anyway, we have already done this question, and see you in the next MIT video.